Today's lesson is exponential growth, and right now we're in our 7-1 notes. Honestly, chapter 7 is chunked into 2 parts, and you're going to have your first test on the first half of chapter 7 already next week. The first half of chapter 7, the topic, exponential functions. And then we talk about inverses again, and the last half of the chapter is logarithmic functions. So you see that the title of this chapter is broken into its 2 parts, exponential and logarithmic functions. Our goal for today is to be able to do 2 things. Graph exponential growth functions. So all of our B values today, based on our Skittles activity from yesterday, all of our B values today are going to be bigger than 1. So today's focus is exponential growth. We're going to talk about how to graph those functions, and then we're going to use the graphs of those functions to solve some real-world word problems. That's what we're doing today. So you have a couple of vocabulary words to go ahead and copy down. The first term for today and our objective for today's lesson, you will graph and use exponential growth functions. That is true. We're going to use those 2 things. Just to go back to a little bit of information from yesterday's lesson, an exponential function, just a reminder, is a function of the form y equals a times b raised to the x power. A can't be 0, because if it is, the whole function goes away. Turns into 0, that's a horizontal line. And the base b is a positive number that can't be 1, because if the base were 1, then you would just, again, have a constant graph. Exponential growth occurs if your A value is bigger than 0 and your B value is bigger than 1. So the growth factor in our formula is going to be B. All right. Whoop. Was that you, Eric? No, who was that? Oh, it was you, Calvin. So next up we talk about the parent function. So while Calvin's finishing copying that, you're going to help me fill in those blanks. You're good? Because we did a good portion of this yesterday with our Skittles activity. It says the function y equals b to the x, where b blank then 1 is the parent function for the family of exponential growth. That's the graph we're talking about today, with a base of blank. The general shape of the graph is shown below. And what we're going to do is we're going to fill in those blanks and then determine the domain and range of that graph. So let's go back. I need a little help. If this is going to be exponential growth, what do you know about that B value? Well, greater than 1 is the symbol that goes in there. Yeah, greater than. Very good, Will. And base, that's just our letter B. Shown below here is just the general graph of y equals b to the x. And we just know that b has to be a number bigger than 1. So you could say it's 2 or you could say it's 3, but we just have a general graph here. What's important to note, we see the first appearance of a very famous word that we talk a lot about in chapter 8. We see the appearance of the word asymptote. And that is not a vocabulary term in this chapter, but it does make an appearance in this chapter. An asymptote is a line that your graph gets very, very close to, but doesn't really touch. It's for this reason that exponential functions are described as asymptotic in their end behavior. Asymptotic just means that there's some sort of asymptote, a line that we get very, very close to, but don't actually touch. And it's actually the x-axis for us here. Why that's important? It affects your domain. So we're going to have to talk about, I'm sorry, I misspoke. It affects your range for these graphs. And then the graph rises from left to right. It does pass through the point 0, 1 and 1, comma b. So I just wanted to talk about, what your graphs always need to have. As we move through Honors Algebra 2, what you're finding is that to get a complete graph, if a problem says graph on your homework, you should always be looking for maximums, minimums, x-intercepts and y-intercepts. Now I need you to look at that graph. Is it even possible to get those things? So let's talk about it. Intercepts. What types of intercepts are you going to have to look for when you look for an exponential growth function in its graph? What are you going to have to look for there? Good, Will. Yes. So you're not going to get x-intercepts. You're going to get y-intercepts. So when you go to graph tonight, because you grabbed graph paper when you walked in, there is graphing to be done this evening. You can tell by the types of problems that we're doing. You're going to have to give me every time the y-intercept. Okay? It's not hard to do. You could look at the equation and figure it out. Do you remember how to do that from last night's assignment? What's the y-intercept, Bree? It's the a value. Nice job. It sounds like you guys are off to a good start in this chapter so far. Well done. Okay, so you always have to graph for me the y-intercepts. There aren't any x-intercepts unless we start to translate the graph, which we'll do on Monday. So for right now, this graph doesn't run into the x-axis. It gets oh so close to it, but doesn't really touch it. You want to know why? I bet you do. Let's pretend this function is y equals 2 to the x power. The x-axis is an equation of the line y equals 0. You know? Y equals 0 is the equation of our x-axis. Are there any numbers you could put in for x to get 0 back out for y? What do you think, Matt? So if you put 0 in, you would get 0 back out? 2 to the 0th power is 1. Yeah, so I'm glad I talked to you. Glad I talked to you. 2 to the 0th power is 1. So yeah, 0 is not going to do it. Are there any numbers you could plug in for x that could get you 0 back out? And you guys are shaking your heads. Yeah, no, there's not. So we can't get 0 back out. This graph gets so close to the axis but doesn't actually touch it. And that's algebraically for a reason. You can't get 0 back out. Doesn't matter what you pick for x. Negative, positive, 0, even fractions, you know, it's not going to work out. So with that, do we have any maxes or mins for the graph? We've been talking about critical parts of the graph. So you folks told me we need the y-intercepts, but do you see any peaks or valleys? Any maxes or mins? What do you think, Danielle? Do you see any maxes or mins? Any peaks or valleys like in a parabola or when we did polynomials? Do you see any of those turns in this graph? That's not a max. If it goes to infinity, that's not a max. You could just say it goes to infinity. But you don't actually get any turning points, so to speak, where the graph goes from increasing to decreasing or from decreasing to increasing. So this thing increases steadily throughout. You're not going to have a max or a min. So really, the only point I need to see labeled, you're like, yes, just the y-intercept for now. So that's kind of nice. All right, let's talk about domain and range of this thing. And then we're done with the blanks. We can go ahead right into graphing. Domain and range. Domain is possible values of x. What do you think? If you're walking along the x-axis, what do you think? Go ahead, Danny. You said it starts at x equals 0, which means it starts right there and goes to infinity? Or are there values over here too? I think you were thinking the range also. Yeah. You could also say all real numbers, but we're trying to get you to write domain and range this way. Okay, so Danny, since you already talked about range a little bit, what do you think the range of the graph is? It is. Do you include 0? Are we allowed to get 0 out on this graph? Very good. So what symbol goes around your 0? A bracket or a parentheses? No, that's if we include 0. Yeah. Remember that the parentheses, I know it's been a little bit since we did domain and range, you use the parentheses whenever you get close to something but can't actually get there. This is why we use parentheses around infinity, because you get close to infinity but you never actually get there. That's the term infinite. So you get close to it but you don't actually touch it, and that's why you include the parentheses. Likewise here, we get this asymptotic behavior, or we have this asymptote right here. We get very close to 0, but we don't actually touch it. So that's why we have parentheses around our 0 right there. Okay, so for right now, what we're going to go ahead and do is we're going to practice graphing now functions of the form y equals a times b to the x. Now, I can look at the function. I'm going to do part A, by the way, and then you're going to practice with part B. You're going to need your calculator also, if you haven't taken it out already, because really, I can only look at the equation and get 1 point out of it as I stand here right now. As I look, I can go ahead and I can establish the y-intercept, or the initial value for this graph. So I can plug 0 into this function, and I get 1/4 back out. That looks a little weird. There we go. And you would graph that point as 0, 0.25, so right there. It's a good idea to label it. And we know that this graph is going to increase. So now we have to go ahead and go to our calculator just to get a couple of other points. So we do y equals 0.25 times 6. Raise that to the x power. This graph. And you'll see that this window's bad right now because I can't see the left side of the graph. So I'm going to go back to Zoom Standard. Okay, so here's my fear. And looking at Zoom Standard right now, it looks like I just have a hook coming out of the x-axis. But that's really not what your graphs should look like. Again, they kind of just get very, very close to the x-axis as they come down. I'm worried that people go to the origin and like put their little like hook coming out of it. I saw that a couple times yesterday. People just like amputating the tail of this graph. So what I want you to see is if you go to the table, you know, right now I'm at positive values, and we see that this thing from the origin does grow very, very quickly. I mean, we started at 1/4, and by 6, you know, by x equals 6, we're already at 11,664. So a growth factor of 6 is very, very steep for an increase. But what you should notice is that just because, you know, you start to plug in negative x values, it doesn't mean that the graph just disappears. It just means that our values got very, very small. So close to 0. So close to 0. So what you're going to go ahead and do is you're going to grab a couple of points. For instance, we have 0, 0.25, and then 1, 1.5. So we can grab those points and put them on our curve there. So over 1, 1.5. But these values shouldn't be ignored either. We just get very, very close to 0. So you want to make sure that your graph has its tail here, that it gets close to 0. What I don't want to see is just things that look like that, because that's not a description of an exponential function. So you can't draw me little hooks coming out like that. And that's really all there is to it. You get your y-intercept, you go to your graph to make sure it's steep enough, and then you just kind of connect the dots. Are there any questions on how I produced this graph? Okay, now you get to try. Part B, that's all you. You know, really, as I go around the room, I do see people plotting their y-intercept at 1/2, and then they labeled that. So that was nice. And then I also saw people, you know, raising 4 to the first power and then taking half of that. So you go over 1 and up 2. So we actually get a nice point there. And then you just have a very low rate of growth down on that negative x-axis. So that's great. Are there any questions about that? Comments, concerns? Notice domain, still all real numbers, or negative infinity to positive infinity. Your range values are just above 0. So you could say 0 to positive infinity for both of these. So the domain and range is still the same as our parent function. We switch that up a little bit next week. If you go to turn the page in your note packet, you'll notice this example is not there. Yes, we already talked about that. So we are going to do this on Monday. But I just wanted to, show you that we're going to talk about h and k. So you need to remember what those do. If it's minus h, you might recall, moves to the right. If it's plus h, it moves to the left. Plus k moves up, minus k moves down. We're going to do that again on Monday, so stay tuned for that. You won't have the homework problems on that. I'll show you the new homework assignment at the end here. Also, part B is missing. I think this little excerpt is also missing, but we're going to use this formula. I am going to get the word problems done with you today. So you're probably saying, where should I write this, Mrs. Lucas? On the next page there, right above example 3, there's like a little space. You could just write the formula just right at the top of the page there. It really doesn't take up a lot of space. So we have a little bit of a description of a formula here. We'll read it together and then I'll tell you what the formula is. It says, when a real life quantity increases by a fixed % each year or other time period in the problem, the amount y of the quantity t after t years can be modeled by a certain equation. What's important to notice here is that our time is typically in years. And that is going to be, you folks know it from the past, that is going to be our control variable for like all of these problems. So when we do our exponential growth functions, they're affected by the amount of time that goes by. So if we talk about growing bacteria in a dish, it's going to be affected ultimately by how much time that dish sits out. Or if I talk about money growing in your savings account, it's going to be affected by how much time you let that money sit in your account. We said it in the past, time is our major control variable. So wherever you see a t, I need you to think about x values for your graph. There's also a couple of other letters, so here's your formula. It goes y equals a times 1 plus r raised to the t power. You might recall from yesterday's lesson, a is your initial amount. And we'll do this formula again on Tuesday. I'll have you fill in these blanks. A is your initial amount. Like yesterday when we did the Skittles activity, everybody started with 50 Skittles. So we had a y-intercept of 50. So yeah, A is always your initial amount, whether it's bacteria or sheep or money. That's the initial amount. R is going to be a rate. It's going to be a % rate of increase, and T is a time, usually in years. We'll have to talk about it if it's not years in just a minute. So we have our first word problem here. I think you do have this example, right, Buffalo? Yeah, okay. So this you actually do have in your notes, and we'll go ahead and read it together. Buffalo, not Buffalo, New York, like buffalo, like big, stinky animals. They're gross. I think they still have them at Boyce Park. They really stink. All right. In the last 12 years, an initial population of 38 buffalo in a state park grew by about 7% per year. In part A, it says, write an exponential growth model giving the number n of buffalo after t years. And then we're supposed to use this equation to determine about how many buffalo were in the park after 7 years. And then you'll see we're going to use a graph. It says graph the model and use the graph to estimate the year when there are about 53 buffalo. So with that, our equation looks a little something like this. Remember, you folks have at the top of your example 3, y equals a times 1 plus r raised to the t power. And we're going to go ahead and write that model for this. So it's going to be y equals a. What is the initial amount of buffalo? Ooh, go ahead, Izzy. It is 38 buffalo. And then I have to do 1 plus my rate. I can explain where the 1 comes from, just not quite today. We actually do go through that in a little bit. Well, it is 0.07. You are correct. It is a 7% rate increase. Ooh, almost wrote it wrong. So you do have to convert that to a decimal. Nice job, Will. And then this does give us the model in years. So our equation is going to be raised to the power of t if it just says write the model. So simplifying your model, you get y equals 38 times 1.07 raised to the power of t. So that responds to that part of the problem. Then it says use this model to figure out how many buffalo there were in 7 years. Remember, years is our control variable in the problem. So we're going to take our time, our t value, and set it equal to 7. And then you need to tell me how many buffalo there were after 7 years. Round to the nearest whole buffalo. Go ahead. So after 7 years go by, how many buffalo are in this park? Yeah, good, Joshua. 61 buffalo, about. They may not get 61. Everybody was able to produce that in their calculator? Okay, so now they want us to go ahead and graph. And today's mission is to use the graph to determine when are we going to have 53 buffalo. So check this out, people. Here's what you are about to do. This is like a landmark day. What we're doing is we're setting our dependent variable equal to 53. And you folks are going to solve for t. You're going to tell me how many years go by before I get to have 53 buffaloes in this state park. That's a big deal. You're solving for a variable exponent. That is it in the end game of this chapter. That is the big thing we do. You get to solve for a variable exponent. We're actually going to do that with logarithms by the end of the chapter. For right now, though, you're kind of stuck using your graph. So until I teach you a little bit more algebra, there is an algebraic way to solve for t. You folks are stuck going to your graph to figure out the answer. So you're going to go to your graph, and you're going to type your equation. Whoa. What did you do, buddy? Go. And you'll see that Zoom Standard really doesn't make much sense for this particular graph. You could use the window that they gave you. I think the x values they have you ticking off go all the way out to 10 years. So on our x-axis, we would go from 0 to 10 years. And ultimately, we want to find out when there's 53 buffaloes. That was my dependent variable, so I need to have y values that include 53. So you could go from 0 buffalo to maybe 100 buffalo. And I think, you know, going by 20s would get you there. What? I have a typo, huh? Oh, do you see what I did? This happens. Who could pick out my mistake? Danny. Yeah, so, okay, yeah. That wasn't even it, though. I don't think that's why the calculator messed it up. Well, yeah, it gave me like that specific error, so it doesn't know what to do. Like I input my min to be bigger than my max, and I was like, well, what? Which is appropriate. You are always smarter than your calculator. I think this was supposed to be, we said y min should be 0 buffalo, right? And we wanted to go out to 100 buffalo. And I wanted to scale it by 20s. So there we go. Show you how to fix your calculator when you get some errors, when you get a window dimension error like that. Just press window. Chances are you just keyed in your window values wrong. So that was beneficial. Okay, so I need to trace, right? Or you could go to your table. I'm going to go to my table. And I'm supposed to find when I'm going to have 53 buffalo. You can get close. Lots of people coming to visit me today. So after what year are you going to have about 53 buffalo in this park? Sally, this is for you at the end of the period. When are you going to have 53 buffalo? Oh, Calvin. After 5 years. Very good. So you could scroll down on your table here. There it is, 5 years, 53 buffalo. So in there somewhere. And then right now, since you have these points, you know, these are nice points for you to graph because you were responsible for graphing this equation also. And ultimately, yes, after 5 years go by, you will have your 53 buffalo. So that is the answer to the problem. So it kind of stinks for right now. The only tool you have to solve for a variable exponent is a graph. And you just have to trace until you find the y value that you need. And then you just write down the requested x value. So that's kind of a bummer for a little while, but it's not always the way it'll be. I'll show you how to solve some exponential equations as we move through the chapter. So you will get another fun tool to use. What's up, Bree? Right. That's ultimately, they're constraining our domain values. So when they say in the last 12 years, so this part right here, they're saying this model is only accurate for the past 12 years. After that, the model is not accurate anymore. So year 13, that data value is garbage. It doesn't do you any good in predicting the number of buffalo there will be. All right, any questions about that? How am I doing? Ooh, is that the end? Looks like it. Okay, so I need to trim down your homework assignment for tonight, right? We're going to finish this section on Monday. We do exponential decay, which is basically the same thing, except our graphs are going to go down. So I do have time in Monday's lesson to finish up what we didn't get to talk about today. However, your assignment for tonight is a little different. Because I didn't get to the translations because the copy center didn't get our note packet quite done the way it should. You're actually doing page 482 still. You're doing 3 to 15 multiples of 3, I think. Oh no, I'm sorry, 3 to 12. And that's multiples of 3. And then there are some not review problems, word problems. For these problems here, 28 to 30, the formula you're going to need to do those is on page 481 in your book. So it's not a formula I taught you today, but there is a formula that you're going to need to work with to do those problems, and the formula is just on page 481. We will talk more about that formula on Monday, but I gave you a couple homework problems to look at just to preview that topic. Okay, so your homework assignment's just a little bit shorter because they didn't copy our notes quite right.